All right, so we're going to continue this with the last in the series on Hopfield networks and Boltzmann machines. Here's a quick recap of everything that we've covered so far. A Hopfield network is a loopy network where the connections between neurons are bidirectional. Specifically, we are considering symmetric bidirectional connections in this case, but this is not a requirement. Each neuron responds to the local field at the neuron, which is the affine combination of the outputs of the other neuron, and tries to align its own output with the sign of the local field. We are assuming, of course, that the activations of the individual neurons are threshold activations. So the way the whole thing works, each neuron senses a field at its location, and if the field is positive, the neuron sets itself to a positive value by +1. If it's negative, it sets itself to -1. Basically, it tries to align itself to the local field, and it continues to evolve in this manner, as you can see from this little animation, until this energy that we can a term that we call the energy of the network sort of converges. Now, keep in mind something that may not have been clear from previous lectures is that when the system converges, it doesn't mean it actually stops evolving. So to give you an idea, consider this very simple network. If I've got just two neurons and I have a weight of -1, if I set a +1 and a -1, what happens over here? Does it stay stable? In this particular case, it actually stays, the field here is positive. I should come up with better examples, but it can actually keep evolving depending on how you set it up between many states which have the same energy, right? So the way the network actually operates is that you initialize the network with some pattern, and at each iteration, each neuron sort of tries to align itself with the sign of the local field. The updates can be sequentially or all at once, and convergence happens when this energy doesn't actually change anymore, right? So the network evolves until it arrives at a local minimum in the energy contour. All of this we have seen. We also saw that this was actually a content-addressable memory, in that if you call these energy patterns the local minima, the configuration of the network and the local minima patterns that you would like to recall, then if you initialize the network somewhere in the vicinity of this pattern, it's going to evolve and recall this entire pattern. So this is also called associative memory, because you're associating entire regions of the state space with specific patterns. And we saw some examples of Hopfield networks in action. Here was an original. If you degraded it, it reconstructed this one. Here's another where if you just presented the network, if you generated a network which stored this pattern, when I'm speaking of storing this pattern, it means that I have one neuron for every pixel in this pattern, and the network parameters have been set such that this is a local minimum state, and if you initialize the network with this pattern, it's going to complete it. So the first case, you have a noisy pattern completion. You initialize the entire network with a noisy version of the original pattern and let the network evolve. Here it is pattern completion. You fix the seen bits and only let the unseen bits evolve. Here in this case, you're not going to let these portions of the network change, because you know what their values are, and you're only going to let these guys evolve when they're eventually going to settle down to recall the entire pattern. So we actually sort of address this question: how do you actually make the network remember specific patterns? How do you ensure that, for instance, how do you compose a network that remembers this Chippendale pattern? And we saw that one of the ways you could actually think about the whole process of making it remember specific patterns is to think of it in terms of, if you unroll the network, this just looks like a very deep network where every layer looks just like every other layer. So the learning process is analogous to backprop, as a matter of fact, right? So the network can be trained to remember specific patterns. We've seen this. And we've also gone into some effort to determine that a network with n neurons can be designed to store up to n target patterns, provided they're sufficiently, it can store up to n, it can make n target patterns stationary, but if the patterns are sufficiently far apart from each other in the right manner, then they can also be stable. We saw this. Now, and so the problem of, but in the process you can also store an exponential number of unwanted parasitic memories. These are patterns that you didn't want the network to remember, but it sort of, but they also are energy wells in the energy contour, and so the network also has an unfortunate habit of settling at states which were not patterns that you wanted to remember. These are fake memories. And so the business of training the network was to design the weights matrix such that the energy of the target patterns that you're trying to remember is minimized. That is, there must be in the energy wells. But those of the untargeted, potentially parasitic patterns is maximized. They're not in the energy wells, right? So we can think of this as an optimization problem. This was the last thing we saw in the last class. You can define the total energy of all the patterns that you're trying to store, and this can actually be a weighted sum where you assign greater importance to patterns that are more important to remember and lesser importance to patterns that are less important to remember, lesser weight to patterns that are less important to remember, and you want to minimize this. At the same time, you want to maximize the energy of every pattern that's not really a target pattern. So if this is your energy contour, if you currently have if your current weights result in some energy contour, you want to keep modifying the weights such that the energies associated with these target patterns that you want to store get reduced, and the energies for every other configuration increase. And for this, we could just use a simple gradient descent mechanism, which says that in each iteration, the weight is going to be updated by some positive scaling of this term here, where this term, which is just computed by differentiating the objective here, comprises the difference between two terms. The first is the outer product, basically the Hebbian weight matrix. You can, so if you think of it that way, the sum of the outer products of all of the patterns that you're trying to store. And the second is that it is the sum of all the outer products of all of the patterns that you don't want the system to remember. The difference between these two is the gradient, and you're going to take a step in this, or this is the negative of the gradient. So you're going to take a step against the gradient, which actually results in this update rule. Now we also saw that this has a problem in its basic form. This first term is easy enough. There's a finite number of patterns that you want to remember. The second term, not so much, because you can have an exponential number of patterns that you don't want to remember. And so you go back and look at the pragmatics of it. Do you really need to pull up the energy contour everywhere, or is it sufficient to simply pull up the energy contours where close to the patterns that you're trying to remember, just to make sure that the patterns that you are trying to remember are memorable? Things that are far away, you don't really care. So this led to the modified update rule, where we try to minimize the energy at the target patterns, but subsequently you let the system evolve. When you start it, initialize it at one of the target patterns, and in the process of evolution it's going to arrive at the locus and local energy minimum, which is where the system is going to evolve to from these target patterns, and you try to increase the energy at those locations, thereby trying to make sure that the target pattern has lower energy than its neighborhood. And this is what we actually try to, and so the update rule actually sort of captures this intuition. And we also saw that in the process there's really no energy to raise the entire surface or even every valley. You just want to raise the neighborhood of each target memory, in which case you initialize the network at the target memory, you let it evolve a couple of steps, which goes out into a little distance from the target, and then you can raise that. And if you keep doing that, eventually you're going to make sure that each of your target memories is in a local valley and ends up becoming a memorable pattern, right? So if you think the stochastic gradient descent version of this entire learning rule was that you'd initialize the weights and subsequently until the network is converged or you die of boredom, you're going to sample the patterns that you want to store. And the update rule has two components. The first one is the outer product of the pattern that you've sampled, and the second is the outer product of the pattern that you arrive at when you start from the sample pattern and evolve for a few steps, right? And so this is, and you wouldn't actually have a summation if you're just using SGD. You're going to go down a few steps, and that is the resulting update that you're going to apply to the weights matrix. So this is your update, right? So far so good. Now this is what we've seen so far. Now here is the issue. All of this kind of works, but how well does it work? Here was this original pattern. Here was the degraded pattern that actually presented to the network. If the network had been perfect, then if you initialize the network with this pattern, you would have expected it to sort of evolve into the exact Bugs Bunny pattern over here. But what you get is this variant which has all of these little dots on it. It's not perfect. So why does that happen? This has to do with parasitic memories. Now there are many local minima, and when you set the network at some point, there can even be local minima close to the patterns that you're actually trying to store. And so when you initialize the network, instead of actually arriving at the pattern that you're trying to store, it might get stuck in one of these little dips. And that's going to give me, in this particular case, that there's no assurance that that's what happened. Maybe the network just remembered things badly. But more generally, this is the kind of thing that is likely to happen, that you will get stuck in these little energy wells that you don't want the system to be stuck at, right? And so in that case, you want to escape it. In the process of evolving, you want to escape it. But if you're following just a simple energy descent rule, where every modification is guaranteed to decrease the energy or at least not increase the energy of the system, then if you're out here, there is no way you're actually going to go into this well. You're actually going to end up, you're always going to end up in this poor local minimum, right? So given this, what would a reasonable rule be to make sure that when you're in such a situation, you can escape it and go into the larger well nearby? So how would you do that? There's no learning, right? This is during inference. I've just given you the network, right? How would you do that? Anyone? Yeah. So a simple thing, if you detect that it's converged, you can add some noise and see if it actually comes back to the same place. And alternately, you don't actually have to wait for it to converge. You can say that I don't necessarily always want it to decrease the energy. Sometimes if the change results in an increase in the energy, I'm still going to accept the change of the state. The two are strictly equivalent statements, right? So that's basically what we would actually do. We want to permit change in state even if the energy increases, particularly if the change in energy is small. So remember, what we did over here in the standard thing is, at each neuron, you just check the field and you made the neuron align itself with the field. But implicitly, what were you doing? You were saying that if I flip this signal, flip this neuron, will the energy decrease? And if the energy would decrease, you flip the neuron, right? You can change that rule and say, if I flip this neuron, will the energy not increase by more than epsilon? And then accept it, right? So instead of only accepting decreases in energy, you want to also allow accept small increases in energy. But then just doing it that way sort of makes it deterministically accepting increases in energy is not a very good thing to be doing, right? That means the system is never really going to converge to something useful. So what you really want to do is to convert it to a probabilistic system, in that if there is going to be an increase in energy, you are willing to accept it with a probability that is small. So you're just sort of embodying this in a more rational manner, right? Where does that intuition come from? That intuition actually comes from we're going to go back to spin glasses. So in spin glasses, we are familiar with this. You have this collection of dipoles. There's a field at every dipole, where the field at every dipole is some affine combination of all of the other dipoles. And every neuron, every dipole tries to align itself with the current dipole. And the energy of the system, we have a total energy of the system, which is basically the sum of the energy contributions of each of the dipoles, where the contribution of any dipole is simply the negative of the product of the dipole with its local field, right? And we said the dipoles would keep flipping until the energy of the system sort of converges to some local value. But is this what really happens? We are familiar with physical systems, right? Do physical systems evolve in a deterministic manner? They don't really. When I gave you this example, I was actually lying. So what happens is that at any shape, if a system is at a temperature that's greater than 0 degree Kelvin, it's never going to be just stable. It's actually going to be bouncing around. It's always changing state. In fact, this is why the whole, the universe is eventually going to sort of dissipate or collapse, or something bad's going to happen, because the system is not at 0 Kelvin. It's always changing state. And so what happens is the amount by which the system keeps flipping between states is dependent on the temperature of the system. The higher the temperature of the system, and we know this from your physics, the more you raise the temperature of the system, the more things keep changing. Yet at each temperature there is an equilibrium, right? So what really happens, what this is characterizing, is not the actual energy of the system. I mean, it characterizes what the energy of the system is at each time, for any state, exactly how we will see. But what you're really getting is a system which likes to keep flipping between different states. And the system will flip between different states with a probability. And the probability of being in any state is going to be dependent on the energy of the state. This is the physics of the system. Now, how does the physics actually work? You might have seen this in your college classes. At that point, maybe it didn't really imprint on you too strongly, but it's a very beautiful thing. So a thermodynamic system at temperature T can exist in one of many states, potentially infinite states. At any time, the probability of finding the system in some state is a function of the state itself, some Pt of s. It's also, I have this T because I'm going to show that this is also probability of function of the temperature. So the internal energy of the system is really, which represents the capacity of the system to do work, is the expected value of the energy of the state that the system is in. So which means that if you have some energy Es associated with each state, but the system is bouncing around between different states with different probabilities, then the expected energy is going to be the weighted sum over all states, where the weight itself is simply the probability of finding the system in that state, right? This is just straight up expectations. This is what the expected energy of the state is. This is what we will call the internal energy of the system. This is the capacity of the system to do work. But then there's something that actually counters the capacity of the system to do work. And what is that? Temperature, entropy, right? If you raise the temperature of a system, you have less control over the system. It's bouncing around crazily. This is where the notion of entropy actually comes to us from, right? That there's an internal disorder in the system, and the internal disorder has to do with temperature. Basically, if you have a probability of a distribution over states given by Pt of s, the entropy of the system is simply minus summation over all states P of s log P of s, right? Now this is the interference that the system actually suffers. The stochasticity of the system actually imposes on you. If the system is bouncing around randomly between states with a probability distribution, this bouncing around interferes with your ability to actually extract work out of the system. Whereas this guy quantifies the overall ability of the system to do work, right? So the Helmholtz free energy, which actually measures how much useful work can be derived from the system, is the difference between the capacity of the system to do work and what is sort of what it loses because of its natural internal entropy, which is the capacity minus, see this product over here, this is the Boltzmann constant K times the temperature, and the larger the temperature, the more the stochasticity of the system is actually going to interfere with its ability to do work, right? And so useful work. So if I hold a system at a specific temperature, it's going to keep bouncing around between states. But will it always keep bouncing around between states in a random manner? No. The probability with which it visits different states is slowly going to converge to some point. And what it happens is that it's going to keep reducing this Helmholtz free energy. It's going to keep reducing the energy of the system, which is what they always do, right? Essentially, it's reducing its potential energy until it arrives at a probability distribution over states where this potential energy is minimum. When is that minimum? That's when this term is minimum. And we can sort of easily enough derive this. You can say, which is what? I have my F is summation P T of S Es minus Kt summation over S again Pt of S log Pt of S, right? Is it what it is? If I want to minimize this, what would I do? I differentiate it with respect to the temperature and equate it to 0, right? So if I do that, dft over dpt of S is going to be Es for any particular state minus Kt, and what is this guy going to be? That is going to be log Pt of S minus plus 1. Is it right? Is that the correct answer? Right? And if you actually work this out, this equals 0. Implies, what is that? Log P is going to be Es minus 1, is it? Yes. I might have some signs missing. So P is proportional to e raised to Es minus 1, or some constant times e raised to S, right? This is basically what you're going to get. Is there a minus? I'm missing a minus somewhere. So if you, actually, this is right. So if you work this out, this is basically what you will get. If you minimize this with respect to S, you're going to find it's actually going to be, there's a Kt. I cannot forget this Kt. So where did my chalk go? Divided by Kt, right? And so what happens is that you naturally get this distribution. When the system actually arrives at a minimum, you're going to find that the probability distribution over the states. Again, you can redo this math yourself. I'm making a few mistakes, but it's trivial math. When you actually minimize the energy, it's actually going to arrive at this probability distribution over states, where the probability of being in any state is proportional to e raised to the negative of the energy of that state, divided by a factor which is proportional to the temperature. So there's this external constant, which is a normalizing constant, which makes sure that the whole thing is a probability distribution, right? And now observe over here that if the temperature is not 0, then regardless of the energy of the state, an energy associated with the state itself, at equilibrium, the system is going to keep bouncing between different states with this probability distribution. Eventually, when the temperature becomes 0, the system is going to be in only one state, which is the minimum energy state, right? So only when the temperature is 0 Kelvin is the system completely stable at the minimum energy state. At all other times, it's going to be changing, it's going to be switching between the different states with a probability, where the probability of any state itself is proportional to e raised to minus the energy of the state divided by temperature, right? So the evolution of the system is actually stochastic. It's not deterministic. It's not just going down to the valley. This is at equilibrium, the system visits various states according to this distribution, which is called the Boltzmann distribution. And the probability of any state is inversely related to its energy, and it's also related to the temperature. Basically, the probability of being in any state, S, is proportional to e raised to minus Es over kT, where the most likely state is the state for which Es is largest, right, or smallest. So if Es is 0, then that's when the this term is largest. As the energy keeps increasing, that term keeps falling. So the most likely state is the system with the lowest energy, right? This is a physical system. So what we are going to do with our Hopfield net is we are going to sort of emulate this process. Remember that our Hopfield net itself sort of emulates spin glasses, right? So we're just going to take the analogy one step further and actually impose the physics of the thermodynamic system on the Hopfield network itself. What we will do is to mimic the spin glass system. So we're going to say the Hopfield network models a probability distribution over states. So every state has an energy, and we're going to say that the probability of finding it in any state is proportional to e raised to minus energy for that state. This denominator is just a normalizing constant that makes sure that all of the probabilities sum to 1, right? So the state is a binary string, and observe that this is just a Boltzmann distribution, right? So what we would do is we can just sort of let the system evolve, and the probability that it's going to, and after it's evolved for a large enough time, it will arrive at equilibrium, and the probability that it will be in any particular state, and we're going to let it evolve according to some specific rules, and you say, and eventually the probability that it will be in any state is given by this formula. Now let's see how exactly this works, right? So this actually ends up being a generative formula model, meaning it generates states according to this probability distribution, meaning if you just sample let the system evolve and begin sampling states, then the probability of finding any state is given by this formula. Finding it in any state is given by this formula, right? Now it looks complicated, but once you get down to the mechanics of it, it just ends up becoming very straightforward. How so? So consider two states. One of them is like so. So let's say I have this 5-state network. Have I got everything? Right. So let's say I have this 5-state network, and so and these states are in values A, B, C, and D, which is each of which is either +1 or -1 in both cases. But in one case, this guy has value +1, and this guy in the same case is the same one, same sequence with value -1. Okay, so if you consider the energy of the first state, the energy of the first state actually has contributions from all of the edges that don't involve this guy, plus the contributions of these terms. So I can write this as -1 times summation j w, this is let's call this the ith node, ij sj, plus something, And this guy, again, for this one, the contributions of all of the terms that don't invoke this particular node are going to be the same for both of them, right? So for the energy for this one is going to be plus 1 times summation j wij sj plus whatever, right? Now, so now the probability that the system is in either of these states is going to be the probability of all of these, joint probability of all of these states, which is the probability of these states times the probability of this guy given the remaining states, right? That's going to hold true for both. So you're going to find the probability of s equals 1 given all the remaining states times the probability of the remaining states for the first case. For the second one, it's going to be the probability of s equals minus 1 given the remaining states times the probability of the remaining states. So if I take the log of these two probabilities and take the difference, this term just goes away because it's common to both, correct? So the probability of that simply becomes the log of the probability of s being 1 given the remaining states minus the log of the probability of s being minus 1 given the remaining states. And this term, of course, we know is just 1 minus this term, right? So I can write the whole thing as log of p of s equals 1 given the remaining states divided by 1 minus p of s given 1 being 1 given the remaining states. Easy. So what exactly, I'm just reintroducing the B's. So this one is, now the energy for any state has a bunch of contributions invoking all the states that are not all for any configuration, has a bunch of terms invoking all the nodes that are not the ith node, the star here, plus the contribution of the ith node itself, plus maybe the bias at the ith node. If I also introduce the bias, that's also going to be minus 1 times bias, right, over here. And this is going to be plus 1 times bias at the ith node. So this is going to be plus bi, and over here it's going to be the same term, except these two terms now have a negative sign, right? The difference between but the log of the probability for any state is simply, as we saw from here, the negative of the energy for the state, right? The denominator is the same for the two guys, so the denominators will go away. And so the difference between the log of the energy of this state, where the s takes value 1, and the log of the probability of this state where s takes the value 1, and the log of the probability of this state where s takes value minus 1, is simply going to be the difference between these two guys, which ends up, if you go through the arithmetic, of just the field at the current node. That's all it is, right? But once you do this, everyone with me? This is very straightforward. There's nothing particularly complex over here, right? But then here's what I have. This is log of p of s equals 1 given the rest of the terms, divided by 1 minus p of s equals 1 given the remaining terms, equals whatever my affine combination, right? So if I work through this, then I'm going to say if I exponentiate both sides, then I'm going to get, say, p over 1 minus p equals e raised to a, right? Which in turn is going to tell me p equals 1 minus p times e raised to a, or p times p plus 1 minus e raised to a equals e raised to a, right? Implies p equals e raised to a over 1 plus e raised to a, which is the same as saying 1 over 1 plus e raised to minus a. Right? So applying this little bit of arithmetic over here, what you're going to get is that the probability of, what was P over here? P was the probability that the state takes the value 1 given all the remaining states, right? And just working through the arithmetic, something magical happened. It turns out that the probability that any given state takes the value 1 given all the remaining neurons is simply a logistic function computed over the field at that neuron. So this very complicated looking bit of arithmetic ended up with giving you something very, very, very familiar, right? And so basically for every one of our neurons, you're going to compute at the neuron the field at the neuron, and we're going to say the probability of the finding the neuron in state 1 is given by the logistic computed over the field. So now, first try, I'm going to redefine my Hopfield network as a stochastic system in order to escape these local minima. Instead of saying each neuron is deterministically going to change only if the change results in a reduction in the energy, right? I'm going to say instead that each neuron is going to take the value 1 with this probability, right? Now observe that I'm going to say 0 or 1 instead of minus 1 or 1, simply for convenience, okay? So now the Hopfield network is simply a probability distribution over binary sequences. The conditional probability of individual neurons in the network is now a logistic function. And here's how we're going to do this. You'd initialize all the neurons, then you'd cycle through the neurons and randomly set the neuron to 1 or 0. Instead of 1 or minus 1, I'm just using 1 or 0, according to this logistic function, where for each neuron you fix the other guys, you compute the field, compute a logistic of the field, and decide whether you're going to flip the neuron or not. And you keep cycling through this until convergence. Now remember, this is a stochastic network, right? So even at convergence, the thing is going to keep flipping through the states, just like your Hopfield network, like your spin glass. The only thing that happened is that states with the lowest energy are much more likely to be visited than states with other energies. But in a very large system, you have so many states that even though the state with the lowest energy has a very high probability compared to the other states, in absolute terms it might still have very low probability. So if you have 1,000,000 states, then the lowest energy state might have a probability of 10 raised to minus 5. And it's still going to be much, much more likely than the other states, but then the probability that you're actually going to visit it a sufficient number of times to identify that this is the memory I'm trying to recall has got to be low, right? Once you introduce stochasticity into the whole process. You take it one step further. Now I can actually think of this as a system that's being cooled. So instead of just using my affine combination as the field, I can divide the field by a term T, which I will call the temperature, much like the spin glass system. And now the probability that any neuron is going to take the value 1 is going to be a logistic computed on this modified field, where the field is being divided by a temperature term, right? And now what happens? I can start off at some temperature. If I'm starting off at a high temperature, even if I'm in a global minimum, there's a very high probability that the system is going to keep flipping out of it. And then I can begin reducing the temperature bit by bit by bit by bit. And eventually, when the temperature actually hits 0, you find that the system, so this guy, the first time quantifies the energy difference you get by flipping a bit, right? If the energy difference due to flipping a bit is not large, then the neuron is going to flip. And if the energy difference is 0 between two states, then the neuron is going to flip with a probability of 0.5, right? This temperature parameter, if I increase it, it moves the probability of the bits flipping towards 0.5. If temperature is infinity, right, then this whole thing becomes 0. And so the probability of any bit flipping is completely random, regardless of what state you are, regardless of the actual innate energy configuration of the states. On the other hand, if the temperature is very small, if it's 0, if the temperature is infinity, right, this thing becomes 0, and so the things are going to keep flipping. On the other hand, if the temperature is 0, it's only going to pick the lowest energy state. It actually deterministically becomes a Hopfield network, right? And so now this gives us this very nice mechanism for actually letting your content-addressable memory recover good memories while escaping spurious local minima. We seem to have imposed a lot of probabilistic math on top of a very simple machine, but when things worked down to it, nothing changed. Instead of simply looking at the field and seeing if the input aligns with the field, which is like using a threshold function, what we did was we replaced the threshold function with a sigmoid, right? Which is what we learned to do in the very first class. You replace your threshold function with a sigmoid. You get a softer version of your decisions, right? Very beautiful. And so here's how the thing works. If I don't have a temperature, I'd initialize the network with an initial pattern. Then I'm going to go through the neurons, and at each neuron I have a probability distribution whose probability of parameter p is given by the logistic function computed on the local field. And I'm going to choose the actual current value of the neuron based on this by drawing from this distribution, right? Now this is evolving, right? So when do we stop? What is the final state of the system, and how do we recall a memory? Let's first look at how we recall a memory. I just let the system evolve to equilibrium. I'm going to just keep letting the system evolve, and eventually you expect it to visit low energy systems much more frequently than high energy states. So after it's evolved for a long period of time, I can assume that it's in equilibrium. I can observe the system over several steps and compute the average value of each neuron. And if the average value exceeds a threshold, it means that that neuron is being set to 1 more frequently than it's being set to 0. So I set it to 1, otherwise I set it to 0. Now there's a problem with this particular setting in that you're actually computing the more likely value for the individual states, but it doesn't mean that the pattern that you get over all of the neurons is a valid pattern, that it's a more likely pattern overall. It just means that you're setting the more likely value for each neuron. To make sure that it actually gets a complete pattern that's also more likely overall, what you would want to do is to actually introduce this temperature term and repeat this process and let the temperature slowly go down to 0. And so what this happens is that its network keeps jumping across energy states, even if they are valleys. But then as time passes, the jumps become smaller and smaller and smaller, and eventually it stops jumping and only goes towards lower energy states. And it's eventually going to end up at a global minimum. And in fact, you can prove that if the temperature decreases slowly enough, this is guaranteed to find you the best memory, the global minimum, right? But even otherwise, it's going to find you a local minimum. So this is what we call annealing, and this is sort of based on the principle of annealing in thermodynamic systems. So the term annealing that you will encounter when you're doing optimization, for instance, comes from this. This paper itself was drawn, was in turn motivated by Metropolis and Hastings paper, and the Metropolis Hastings paper is was published in the 50s in a journal on chemical engineering. It doesn't actually appear anywhere close to computer science or math. So anyway, we can use this. If you want to just to complete a noisy pattern, you'd initialize the entire network and let it evolve in this manner. If you want pattern completion, then the bits that you actually No, you're going to fix those and only let the remaining bits change, right? But the whole process is still going to work. And when do we stop? Again, we'd stop when the energy of the system, or since you're thinking of this as a probabilistic system, then the likelihood, the probability of the states that it's generating sort of tapers off, right? So here's a recap. Stochastic Hopfield networks. The probability of each neuron is given now by a conditional distribution. But then what is the probability of the entire network taking any particular configuration y? That is simply given by this term over here, right? We figured this. And so when you're minimizing this energy, it maximizes the log likelihood. And so if you want to see when to stop, you just want to see when the log likelihood of the patterns that you're computing is minimized. This whole thing has now converted your Hopfield network to a stochastic machine. And specifically, the stochastic machine is using a probability distribution, which is basically your Boltzmann distribution, but without the Boltzmann constant, right? So we're going to call this a Boltzmann machine. Okay? The entire model can also be viewed as a generative model, in the sense that if I just start the network randomly and then let it evolve for a very long time, if you sample it, the probability of finding it in any state y is simply given by this formula over here. So it's actually able to generate samples from this distribution as well. It's a generative model. How do you train the network? We've just spoken of how do you escape local minima, right? We sort of took this machine, which is very deterministic, added a lot of very funky math, and ended up with something that looked very familiar, which was just replacing your threshold function by a logistic and then flipping a coin. And it gave us a way of escaping local minima and getting to global optima, right? But the bigger problem is I want this network to remember specific patterns. If I change this whole network into the stochastic machine, presumably this changes the manner in which I actually learn the weights to make it behave the way I want it to behave, right? Or does it? So to understand what happens over here, let's go back. Here is the energy of the system. I've sort of ignored the bias again, because the bias can be thought of as just one neuron, which is a fixed value of 1. Okay? The probability of finding it in any state is just this Boltzmann distribution, where inside this, instead of writing the n minus E of s, I've explicitly written out the energy, which is the summation over all pairs of neurons of the weighted sum of their products, right? The weight itself is the weight, is the weight of the edge connecting the neurons. When you train a Hopfield net, you must learn these weights to remember target states and to dislike other states, right? So similarly, when you train a Boltzmann machine, you want to learn the weights to assign a desired probability distribution to the states, but the desired probability distribution must be such that it's going to assign high probability to the patterns that you want to remember and very low probability to the patterns that you don't want it to settle in, right? So it's basically the same statement, but I'm making it from a probabilistic perspective. So if you're given a set of training instances S1 through Sn, you want to assign higher probabilities to patterns seen more frequently. You want to assign lower probabilities to patterns seen less frequently in your training instance, and you want to assign lower probabilities still to things that are not in the set. Make sense? Right? We're just sort of restating what we did in terms of energy, now in terms of probability. And the way you can do it is I can compute the log probability. I can compute the probability, joint probability of all the samples that I have provided for training, and the log of the probability of any given pattern, as you can see over here, is simply going to be the log of this guy, which is simply this argument over here minus the log of this normalizing constant, right? So the log of the probability assigned to any given state is simply going to be the energy for that state, or this I find it's a negative energy, but this term, the weighted sum of all of the products of the states, minus the log of this second term, which is computing, which is the normalizing term, which makes everything makes this a probability distribution, but it's actually summing over all possible state sequences, the exponentially large set of state sequences, right? So if I give you a bunch of training samples, I can define the average log likelihood over the entire set of training samples. And now I can think of learning my weights to maximize this log likelihood. If I maximize this log likelihood, it's naturally going to maximize the likelihood of the states that I want to see. And this is going to naturally come at the cost of the states that I do not want, because those guys occur in the denominator, right? So I'm going to take the average of this term over all of the states in my training set, which it turns out is going to be the average of the first term over all of the states in my training set, minus the average of the second term, but because the second term is not really a function of my training set, the second term itself doesn't change. Averaging this over n samples is going to be summing n once and dividing by n. The averaging operation goes away, right? So this log likelihood is the average of this first term, which is basically the weighted sum of the pairs of states, every pair of states, minus the log of the normalizing constant, which is the sum over all exponential sets of states of the exponentially large set of states of the exponent of the energy associated with that state, right? Now, how do I actually minimize this? This is a complicated function, but I can minimize this using gradient descent. Or I can maximize this using gradient ascent, because I'm trying to maximize the likelihood. For this, the first thing I need to do is to compute the derivative of this log likelihood with respect to the weights. So let me compute the derivative of the log likelihood with respect to any wij. For the first term, when I take the derivative of the log likelihood with respect to any wij, all that remains is simply going to be the average of the products of the states, right? Because this you have wij, si, sj, right? So if I take the derivative with respect to wij, you're just going to be left with si, sj. So for any particular weight, if I take the derivative of the log likelihood with respect to that weight, all that remains from this innermost term is going to be si, sj. The summations stay. This summation goes away because you're choosing one specific weight, right? And the outer summation over all of the training instances and the division by the number of training instances stays. So this first guy, as you can see, this just looks like a Hebbian learning group, right? The more complicated, anybody lose me with this first bit, right? This is the easy bit, okay? The more complicated one is the second term. What is this guy? What is the derivative of the second term with respect to the weight? So the derivative of the log of the sum of the exponent of the sum of the weighted products. The first thing, this term itself is going to end up in the denominator, right? Then for any specific weight, the summation over all states of course is going to stay. So I get the summation over all of the states in my training set, all of the states, not the training set, all of the exponential number of states, right? Then because this is an exponent, the exponent also stays. And then finally you take a derivative of the argument of the exponent with respect to the weight. That's simply going to give you the product of the state values itself, because the W goes away. Right? What is this term over here? This guy is simply the probability of the state, right? So in other words, this derivative simply ends up being the expected value of the products of the two states, where the expectation is taken over the entire state space using the Boltzmann probability for the state. Right? The problem here is that to compute this, you have to sum over every possible state. There's an exponential number of these states. So instead of doing this, what is the alternative? If I want to compute an expectation of a probability distribution, and if this requires drawing, impossible computation, then the standard trick, we just sample it, right? And so we can estimate this expectation as the average of samples drawn from the distribution. I can just draw samples from this Boltzmann distribution, m of them, and take the expectation. How do we draw samples from the Boltzmann distribution? We've already seen that the Boltzmann distribution, the Boltzmann machine is a generative model. If I just let it run, eventually after some time, if I begin taking snapshots of the machine, it's going to give me samples from the Boltzmann distribution, right? And so I can initialize the network randomly and let it evolve by probabilistically flipping coins according to the for each state, right? And then after many epochs, I take a snapshot of the state. I keep repeating this process, and each snapshot is going to give me one draw from the Boltzmann distribution. I'm calling this S-simul to say these are simulated estimates, right? And then subsequently, this expectation I can just take as the average over all of the samples that I've drawn by simulation, right? And so now, here's what we get. We are looking at a gradient ascent rule, correct? So the gradient ascent rule is going to be, you initialize the weights. So when I initialize the weights, I've started off by creating an initial Boltzmann machine. But then, using the initial weights, this term of course doesn't depend on the current set of weights, right? This second term is what depends on the current set of weights. And this second term you're going to draw by just letting the current network run several times and drawing samples from it. And then the overall derivative is going to be the difference between this first term and the second, which is the average of the products of the sample values that have been drawn from the Boltzmann distribution. And then finally, you would update your weights using a standard gradient ascent rule. The math there's nothing complex about it. It looks a lot more complex than it really is, right? We're still working with the Hopfield network. We just sort of probabilisticized it. Now, something strange has happened here, right? In the process, do you see this formula over here? Does this formula look familiar? What does it look like? Anyone? This was exactly the same as the formula we used to update the weights for the Hopfield network. Nothing changed, right? I went through all of this very complicated machinery. But what were we doing? Maybe I can find the figure. This first term is basically the average product for all of the target states that you want to get. The second term is simply, you want to pull up every single state, but you know that you cannot pull up every single state. Even when we were training the Hopfield network, what did we do? We sampled, right? We just let it randomly evolve and got samples. That's basically what we are doing still. The only thing that changed was the manner in which you got these samples, which was that you initialize the work, now waits, you let the network run, you got a collection of simulated state samples, you computed the gradients and then updated the weights, right? Absolutely nothing changed. So all of the magical statistical machinery, gave us back the original machine with just one small change, which was the manner in which you drew the samples. Questions? Right? So lots of complex stuff, but eventually when you look at it, it's very straightforward. It's just a regular content addressable memory. Now, we know the network can store up to n n-bit patterns, right? Regardless of how you do it. Can we actually increase the capacity of the network? And we saw how we can do it in the last class. I can append to it a whole bunch of don't care bits. And if I append a bunch of don't care bits to it, the new capacity is n plus k. But we only are interested in the pattern of these neurons. These are the don't care neurons, right? So we will call these the visible neurons. These are the ones whose patterns we're interested in. These are the hidden or the invisible or the don't care neurons, right? They only serve to increase the capacity, but the actual value of the neuron itself is irrelevant, right? Which means this can be set to anything in order to complete a visible pattern. Now, when I'm appending bits to a visible pattern in order to increase the network's capacity, then there are any number of hidden patterns, 2 raised to k hidden patterns that I can append to this guy, right? Which of these do I actually choose? Ideally, I want to choose the one that results in the lowest energy for the extended pattern. That's how I can guarantee that it's actually a memorable pattern, right? But that's an exponential search space. Alternately, I can consider that I can have multiple hidden patterns for each visible pattern. That way I actually create multiple minima for each recalled pattern, making it more robust. But then I still have to figure out how many copies do I make for each visible pattern? How do I set them? So instead of thinking about it this way, why don't I say, I'm not going to specify the hidden pattern for each visible pattern, I'm going to consider all of them. What do I mean by saying I consider all of them? Look at this. This is the basic Boltzmann machine, right? With no hidden units. I'm going to extend it with hidden units, these guys, right? But now, when I'm speaking of the state of the system includes the state of the visible neurons and the state of the hidden neurons. The state is actually a combination of V, which are the visible neurons, and H, which are the hidden neurons, right? And so if I want to compute the probability of a specific set pattern, visible pattern, I can compute it by integrating out, marginalizing out the hidden states of the hidden neurons from a completely probabilistic perspective. So I'm still working with the Hopfield network, but I'm working with the probabilistic perspective, which makes it a Boltzmann machine, right? And so now we want to set up the network such that the marginal probability of the visible patterns that we are trying to store is maximized. In other words, I want to maximize this guy, the summation, over all the hidden state values for the entire pattern, right? How can I train this network, and how do I do inference on it? Now, again, this is just this regular, this is just the same equation as we had before, except that the probability of a visible pattern is obtained by summing the probabilities of the states over all hidden patterns that correspond to the visible pattern, right? So now if I give you a training set, if I give you a specific visible pattern, the log probability of the visible pattern is the log of this guy, which is the marginal probability of the visible pattern over all hidden patterns, minus the log of the denominator. And what I'm trying to do, I'm still going to try to use the maximum likelihood estimator, which is going to maximize the log likelihood of all of my training instances. All of the training instances which only comprise of visible patterns, they are no hidden, because the hidden patterns are not really provided, right? They're synthetic. Now I can write this out like so, and I want to maximize the average log likelihood of all of the visible bits of the training vectors. But then this is different from the original Boltzmann machine without the hidden patterns, right? In the original Boltzmann machine without the hidden patterns, I didn't have a summation within this log. This was just the energy itself. Now I have the unfortunate situation that even the numerator term actually has a summation over all of the hidden states, right? So when I compute the derivative of this guy, I must compute the derivative of these terms, each of which now has a summation over many terms. But guess what? I don't even need to go through the math. This is very straightforward. What happens here is that if I take the derivative, we know how to compute the derivative of the second term. That's just the expected value over all states, right? What you will get for the first term, you're going to get the expected value over all hidden states given the visible state, right? Consider this. I take the derivative of this guy with respect to any weight. The first thing that happens is that this entire term comes to the denominator. This is the probability distribution of the hidden state, right? Then the exponent term ends up in the numerator. Then I get the derivative of the argument, which just gives me the product of the two states, two S terms. And then of course I have the summation over all of the hidden states. This guy here is simply the probability of this numerator is the probability of the state. The denominator is the probability of just the visible state, the visible portion of the state, because you are marginalizing out H. So you get P of S divided by P of V. That ratio is just P of S given V, right? And so this entire term over here is going to be P of S given V, which is basically P of H given V, over all, summed over all hidden states. So you're really just taking the expectation of, for each pattern that you're given, you're taking the expected value of the product of these states over all the hidden states, okay? And the expectation again, it's over an exponential number of states. You're not going to be able to compute it. What we will do is sample. So this gives us this this modified formula for the derivative of the log likelihood with respect to any weight. The first term, you are taking an average over all of the training samples that you've got, but for each training sample, the term that you're computing is the expected product of the states over all hidden states for that training, for that given visible pattern. The second guy is the expected value of the product over the states of the two S values, the states, over all possible states. And so this term, this hidden term, you're going to be computing it by sampling as before. The second term too, you're going to be computing it by sampling, but then there's a difference between these two guys. This is S given V. This is S, right? So what does this mean? The first, I'm going to use simulations as before, but for the first step, I want to compute the expected value of the products of the state of the neuron outputs when the visible pattern is given. So I'm going to fix this V and then run my Boltzmann machine. If I fix the V and run my Boltzmann machine, eventually the only thing I'm going to be generating is many samples of H, right? And so for each visible pattern, I will be generating several samples of the hidden pattern when I run it. And so now each visible pattern is going to become actually a collection of samples, where in this entire collection the visible portion is fixed and the hidden portion changes. And so my small set of n training samples, if I generate the hidden value k times for each training sample, I'm going to get k of these guys for each one of my training samples. So I'm going to get n times k patterns in all. And that gives me the first portion, this term here, right? For the second portion now, I can just release the hidden pattern because now I want to evolve the entire network, correct? And if I evolve the entire network, I can generate a bunch of simulated samples, and that's going to be a set of give me a set of simulated samples. And then having done that, now the gradient is simply going to be the difference between the average of the products of these two, the derivative of the log likelihood with respect to any weight is going to be simply the average of the product of the two neuron outputs on either side of the weight, the two neurons on either side of the edge. It's actually the difference between the averages of these products under two conditions. The first is when you fix the visible neurons and only modify the hidden neurons. And the second is the average computed when the entire network evolves, right? And this difference gives you the derivative of the log likelihood with respect to the weight. Now you can just plug it in, and you can, this should have been, since I'm maximizing the likelihood, this should have been a plus, right? That's a bug. And then I can just do the gradient and update the weights, right? But then observe what happened over here. This looks just like your Hopfield network, right? All that happened is that instead of specifying what the hidden values were for the Hopfield network, I generated samples. I let it evolve and collect various energies, but eventually the actual arithmetic ends up being exactly what we saw in the last class for the Hopfield network. We just put a lot of probabilistic gobbledygook on top of it. We included, exponentials in the numerator. We included normalizing terms, which by the way are called partition functions. It sounds cool, but eventually it just gives you a Hopfield network, right? So Boltzmann machines are stochastic extensions of Hopfield networks, which enable storage of many more patterns than Hopfield networks, but also enables you to compute probabilities of patterns and completion of patterns. So overall, for training, you're given a set of training patterns which could be repeated to represent relative probabilities. You initialize the weights. You run the simulations to get clamped and unclamped training samples. What do I mean by clamped? Where I fix the weights, the visible portions, and only let the hidden portions evolve. And then unclamped, where I let the entire network evolve. And then from these, I compute the gradients and update the weights, and I iterate the whole process, right? For running pattern completion, if I'm given some of these visible patterns, visible bits and not the other bits, I just fix the ones that are given. I let the entire network evolve without modifying these guys. And then I sample the visible bits eventually when the thing has sort of finished its evolution and choose the most probable value. Or if I'm filling out patterns, so that would be the second case. If I'm fixing degraded patterns, I can initialize the visible patterns and then just let the network evolve and do the same thing as before. Now we can use this for classification. Everything we said, we're just talking about generic settings of networks, right? But how can I use this for classification? Now, I can have a bunch of features, but then I create an extended pattern, which is the set of features which could be real valued numbers which I've discretized. Or there are variants which actually allow you to have real valued features. But then the extended representation includes both features and the class, where the class itself is represented either as one hot or as a binary vector of any kind. And now you can learn a Boltzmann machine which remembers these guys, right? Subsequently, when I give you just the features f, I can fix the features, let it evolve, and I can fill out the class values, and now I can use it for classification, right? Several issues. The whole idea is you have a generative model. We started off with a Hopfield network, and what I should have mentioned way early was that the Hopfield network, although it's a content-addressable memory, content-addressable memories are really also classifiers. They're combination classifiers and regressors. If I give you XY value pairs, I can concatenate the two, train my Hopfield network or my Boltzmann machine, and then later I can fix the X and generate the Y. And when I generate the Y could either be a class or a value, right? So the Boltzmann machine is just a a stochastic extension of this guy. The problem is training takes forever, right? It doesn't really work for very large problems. So how can you fix that? There's a very simple solution called restricted Boltzmann machines. Now in the regular Boltzmann machine, amongst the visible units, every neuron connected to every other neuron. Amongst the hidden units, every neuron connected to every other neuron, and every visible neuron connected to every hidden neuron, and vice versa, right? The thing is fully connected. Let's simplify it. We will say that the hidden neurons don't talk to one another. The visible neurons don't talk to one another. This simple modification greatly simplifies the computation. How so? This was originally proposed as harmonium models by Paul Smolinski. I'm still going to use the same math. I'm going to compute the field at every neuron, and I'm going to use this probabilistic mechanism to decide whether I'm going to flip the neuron or not. But here's how the modification adds a benefit. So during the clamped state, when I fix the neurons, visible neurons, I can only change the hidden neurons once, because those hidden neurons don't come back and modify my fixed neurons, right? So which means there's a one-step process for sampling the hidden neurons. So it sort of eliminates this whole business of things evolving, right? And for that, I'd be using this standard logistic function. Now, if I want to do the unclamped version, I'd be computing the logistic at the visible neurons using the same same formula as before, and I'd be using those to decide whether I'm going to flip them or not, modify them or not. So remember, in the full Boltzmann machine, everything was connected. We first fixed these guys, then sample this one, then we let everything evolve and sample the union and so on, right? That actually gets simplified, greatly simplified over here. What we would do is, what's happening here? Here's how it would happen. Here's what you would do. If I were given a training sample, from the training sample, I would just sample the hidden pattern once. That's all I need to do. That's for the first term in my learning update rule. For the second term, then I can update the visible patterns based on the hidden patterns, and then follow this whole chain for a long time, and then begin sampling the entire pattern out here for the second component, right? And so it turns out that if I want to learn the weight that connects an ith hidden visible neuron to a jth hidden neuron, remember, hidden neurons don't connect to one another, visible neurons don't connect to one another. That's simply going to be just this product at the first evolution minus this product when the whole thing is sort of evolved for a very long time, right? Or you could average this over several evolutions towards the end. But then remember, when you go back to Hopfield networks, we said something very interesting. I said I didn't need to let this guy evolve all the way to the bottom of the valley. I just needed it to evolve 1 or 2 steps. And that pulls up the neighborhood, right? I can use the same trick over here. It actually simplifies things even further. From the visible neurons, I get the hidden neurons, and I can just do 2 or 3 steps of this guy, and then compute my updates after this small number of iterations of sampling, right? And this is sufficient to give you a very good estimate of the gradient. This is the algorithm that Jeff Hinton famously introduced as contrastive divergence. Now, it sounds very fancy when you actually look at how he's explained it, but then if you see the entire sequence of thought, the complete thought process from beginning to end, starting with Hopfield networks, you see how the whole thing is actually a very simple, there's almost a continuous flow of thought from one end to the other. So restricted Boltzmann machines, they're excellent generative models for binary or binarized data. They can also be extended for continuous valued data. There's this very nice paper by Welling et al. In 2004. It's useful for classification, as we saw. It's useful for regression, and it's most commonly used to pre-train models. So for continuous Boltzmann machines, you actually hang stuff off your There are other variants called deep Boltzmann machines, things called Helmholtz machines. Many variants have been proposed in the literature. The deep Boltzmann machine has the structure where the hidden neurons themselves are further layered, but the basic concept still remains the same. If you understand the basic Boltzmann machine, all of these are different structurings of the basic Boltzmann machine, and everything else is going to stay and so you can build up the math for these guys very trivially. Now the one extra extension that you can make is that in all of our math we've assumed that the connections are symmetric. The weight that connects I to j is the same as the weight that connects j to I. If you make the two different, then you end up with these things called the Helmholtz machines, right? You have crazy algorithms called wake-sleep algorithms and so on. All of these are just basic variants of this very basic idea that I just explained, and you can build up everything on your own in just a few minutes, starting from there. So I have sort of missed a few topics like learning and inference over RBMs, mean field approximations, RBMs as feature extractors, more structured DBMs, but there's nothing particularly complex about any of these. Once you understand the basic ideas that we just discussed, the rest sort of follows easily, right? I'll stop here. We are out of time and then beyond. If you have any questions, post on Piazza. I'm going to try to record another lecture on Friday if I can on variational autoencoders, but it may not be possible, in which case that will be recorded at a later time and put up. Okay.